We will start with the first lecture of week number 8, and in this lecture we are going to first look at the functions of an air conditioning system. Then we will look at the classification of air conditioning system according to application, and there are 3 types of central air conditionings that we will look at, and finally we will focus on one of those types, which is the type that is most widely used, and we will go into greater details of that type of a system. So when we look at an air conditioning system, it performs certain functions. The primary function, of course, is to provide the necessary energy for cooling or heating of the conditioned space, but other than that we also need to ensure that the air is properly humidified or dehumidified. It has to be cleaned and purified. That means if there are any airborne particles or contaminants in the air, they have to be removed before it is supplied to the conditioned space. And even the noise levels which result due to the operation of the air conditioning equipment has to be monitored according to our requirement. For example, if you are working on a shop floor which is air conditioned, noise levels which are higher are permissible, but if you are going to provide air conditioning for a library or an office environment, definitely the noise levels over there will be comparatively much lower, and that also has to be taken care of when you design your air conditioning system. Then we need to distribute the conditioned air. That means in the right quantity or volume flow rate it has to be supplied to the conditioned spaces, and within the conditioned spaces we must also ensure that the air distribution is proper. That means that the air movement inside the conditioned space is also proper. Then of course we need to control the environmental parameters within the predetermined limits. We can allow the temperature or relative humidity to vary, but we will set those values that within those values the temperature or relative humidity can vary. If it goes above or below that, then there must be a control mechanism for that. The classification of an air conditioning system, we can do it on the basis of application, that is for human comfort, and that takes various forms. For example, if you are providing air conditioning to the occupants of an office building or a shopping center or a restaurant, that's the commercial sector. You also provide the same air conditioning for educational institutes, libraries, etc. So you have the institutional sector. After that we can also go to the residential sector, that includes hotels or apartment blocks that are air conditioned, and then we have hospitals, clinics, or other healthcare facilities. And finally, of course, the transport modes that include both air travel on roads, on sea. So we have a wide and diverse applications of air conditioning for human comfort. Then we move on to the industrial application, that is process air conditioning, and there are several examples. I've just identified a few over here. For example, in the textile industry, when we manufacture a particular textile or a fabric, the fiber that is used for manufacturing has its properties very much dependent on the humidity and the temperature levels, and those are controlled by using some sort of an air conditioning system. Then we have various applications of air conditioning in the manufacturing industry. One very important example is in the manufacture of integrated circuits and computer chips, which require an exceptionally clean environment and a very precise control of the temperature and humidity levels within that environment. The same applies to production of precision instruments and products, where again even the noise levels which can lead to vibration are to be kept within very strictly controlled limits. A very important application is in the pharmaceutical industry, which has very stringent standards to maintain the quality of your product, that is a medicine or a drug. And so at every step of the production, those standards have to be maintained, because if we allow, let's say, one of the variables, for example the temperature, to exceed a certain value during a certain process, that can lead to a particular chemical reaction not proceeding properly, and that will ultimately lead to a medicine or a drug that will ultimately harm the person who takes that drug. So these processes in a pharmaceutical industry have very strict controls. We now move on to central air conditioning systems, and there are three broad categories, that is all air systems. When we talk about these three categories, we divide or distinguish between them according to the mode of the energy transfer, that is how we are carrying energy from the conditioned space. If it is done solely through the use of air within the conditioned space, that is known as an all air system. And that all air system that we will look at later on requires the use of air handling units or rooftop packages through which the air is conditioned. How these function, you will look at it later. The difference between an air handling unit and a rooftop package is that primarily in a rooftop package the refrigeration system is also present over there, whereas in an air handling unit the refrigeration system is separate and it is located in the plant room of the system. Then we look at the various advantages and disadvantages of such a system, and for large buildings and complexes, this has the greatest potential for energy conservation, and we have very precise temperature and humidity control. Air distribution and ventilations under varying loads is carried out quite well with this, and the noise in the conditioned space is minimized because we have a plant which is located away from the conditioned spaces as required. Of course, it has a certain, you can call it disadvantages, that they take up more space, and if you have to retrofit such a system, that means after several years you have to make changes that may not be always possible. And the balancing of air requires in large buildings special attention, but that is nowadays not that critical much of a problem, because we do it through computerized control systems. Then we have the second type of air conditioning system, which is known as air and water system, and this time we are using both air and water inside the conditioned space for the energy transfer. The water takes away the sensible energy. If we are talking about cooling, it will be chilled water that is used in the conditioned space. If you want to provide heating, then it will be hot water, and the air will take up the role of ventilation, and it will also carry away the latent load, that is the moisture from the conditioned space. And these are systems which work best for what is known as perimeter applications. That means in the exterior spaces of buildings with large sensible loads, and where the control of humidity and is not required very closely. The advantage, of course, is that you can control individual zones by varying the both the air and water flow rates or temperatures. space requirement is somewhat reduced, and the cooling coil is in the conditioned space, but it is dry, so the problem that you will have a condensate that will have to be drained away is not present, and that also eliminates any risks of bacterial growth. Okay, the disadvantage is that operation and control is quite difficult, in the sense that we need to control both the flow rate of water and air and their temperatures, and as I mentioned earlier, they have the usage is suitable for perimeter zones where we have large sensible loads. Then we will move on to the third type, in which we will use only water for carrying the energy into or away from the conditioned space, and they again require units which are known as fan coil units, and they are located in each room of the building, and if cooling is required, chilled water will be circulated inside those FCUs, and if it is heating that is required, you can circulate hot water through those coils, and that is how the all water system works. The air has no role in that sense, that if we require ventilation, the air will have to be supplied from outside through an opening in the wall, and these would work where you would just require individual room control, and again they require less space and they can be easily retrofitted. Individual room control is possible, and because in winter the temperature of the water that is required is not too much, we can also make use of solar or waste heat for that purpose, and simultaneous heating and cooling is possible with what is known as a 4-pipe system. That means there will be 2 coils, one which can carry hot water and other which can carry cold water, whereas there is also known as another system which is a 2-pipe system. So at one time you can either provide chilled water or hot water. The disadvantage is that maintenance costs are higher, and draining of the condensate can be a issue at times, and that can lead to health risks, because bacterial growth can occur if the condensate water is not properly drained from the conditioned space. Ventilation can be a issue with these, because we are just relying on the outside air, and especially when we talk about summer and humid climates, then it may not be suitable to use these sorts of systems. The most widely used system is the all air system, and that is the type of system that we are now going to look at, and we will go into more details of the all air central air conditioning system. These are systems for large area buildings with many zones of conditioned space. That means when we say a zone, a zone is not necessarily a single room, it can be a collection of several rooms, but they all have the same operating characteristics. And then you can have large area buildings where we have several zones which have their own operating characteristics, and for that we can use central air conditioning system of an all air type. And the all air system will have subsystems, one of which is the air system. Remember, we are using air as the only medium which is used to condition the space, and the components of a air system include the air handling units, the ductwork for supplying the air and returning the air from the conditioned space or spaces, and there are various terminals or VAV units. VAV stands for variable air volume. We will look at that as well later on. And of course, when the air is supplied to a room or a space, we have to diffuse it, so the air movement in the conditioned space is also done in a proper manner. And then we also need a exhaust system for maintaining the desired indoor air quality. We exhaust part of the air from the conditions returning from the conditioned space, and then mix the recirculated air with the fresh outside air. We will also need in this type of a system water, and that water is supplied to what is known as the air handling unit. And the water that we use in the air handling unit can be either chilled water or hot water, depending on our requirement. In winter we will be using hot water to heat the air that passes over the heating coil in an air handling unit, whereas in summer we will be supplying chilled water to the cooling coil for cooling the air that passes over that coil and subsequently goes into the conditioned space. As I said earlier, we have a central plant which is separately located, maybe in the basement of a building, or it could be a even separate facility away from the building as well. And that is done to ensure that the noise of the equipment in the plant is not transmitted into the conditioned spaces. We have access for the personnel working in the plant for maintenance purposes, etc. And the central plant will house the refrigeration plant, which is also known as a chiller package. You will have that will ultimately provide you with the chilled water. You will have the boiler plant that will provide you with the hot water or maybe even steam for winter air conditioning. And we will have pumps for the water, for circulating the water, and also we might have a water cooled condenser for which there will also be a water circuit for that. And finally, these are now large systems and they require control through a control system. We have controls which are now microprocessor based, and we have various sensors which can be temperature gauges, can be humidity measuring sensors, pressure gauges, and we have a central control system. Outputs from these gauges and sensors allow the operation of various components of the system. For example, if you want to increase the flow rate, you will actuate a damper, or if you want to increase the flow rate of water, we will have to open valves, and that can be done through control systems. This is the schematic diagram of a central air conditioning system, which is an all air system, and we have the central plant. So you will have the central plant which will house the chiller, that is the entire refrigeration unit. You will have the boilers, you will have the pumps, and if you have a water cooled condenser, you can see the circuit for the cooling water that goes to the cooling tower is also shown over here. Then you have the air handling unit, and from the air handling unit the conditioned air goes through the supply ducts into the conditioned space where it will be distributed through diffusers, and then the air from the room will be returned back through return inlets back to the air handling unit. What we can do is look at what is happening in the plant room, and then we will move on to the air handling unit. So in the plant room, if you are talking about summer air conditioning, we will be sending chilled water to the cooling coil of the air handling units. So the evaporator serves to chill the water, which is pumped to the cooling coil, and what we will have is that air will pass over this cooling coil and it will cool down, give up its heat energy to the water, whose temperature will increase, and that water will return to the evaporator to be again cooled and then return back to the cooling coils. So that is the loop that we are looking at over here. If you follow the movement of the cursor, that is what is happening over here. And in the air handling unit, you have the air, the supply air. We will start from the supply side, then you will see we will come back to the air handling unit. It goes into the conditioned space, and then it will take up the load from the conditioned space. It will be returned, and when the air is returned, part of it is exhausted. So we have the exhaust air over here, and then the remaining part is passed through a damper. The damper controls the volume flow rate of the air that is exhausted, and then the volume flow that will be allowed to go through into the downstream side. And we will then bring in outside air to mix with the recirculated air, and that will give you the desired indoor air quality. And that air will then pass over the cooling coil, and there's a fan to ensure the air movement through the entire system. That fan will then supply that air to the conditioned space. So that is how it will work. If you are talking about winter air conditioning, then instead of the chilled water loop, we will have the hot water loop in operation. We have a boiler over here. The hot water goes to the heating coil. If required, we can also provide humidification by a humidifier, and the hot water will, when the air passes over it, the hot water will give up its heat to the air, which will warm up, and the water will then return to the boiler. So the heated air will then, if required, be humidified. Then it will be supplied to the conditioned space, and again, as before, it will be returned to the AHU. Part of which of that air will be exhausted. The remaining will be mixed with the outside air. So this is the basic working of a central air conditioning plant. Of course, in large buildings, it's not necessary that you have just a single AHU. You can have multiple AHUs, which are all connected to a single plant for that central air conditioning system. We will now look at another view of the AHU, and you can see all those panels. Like it's like a large cabinet with access panels that allow you to service various parts of the AHU. So you have dampers, you will have blowers, you will have filters, and the heating cooling coils. So that is how an air handling unit would look like, and I will show you an actual photograph of an air handling unit, and then we will also look at a video showing the use of AHUs in a central air conditioning system. So I will just show you a photograph of an AHU. This is from the company known as Daikin. So it's one of their models of the AHU. You can see it's like a cabinet with the access panels open, and if we start from over here, this is the supply air that will go to the conditioned space, and you have the return air. So we start from over here, the return air will come in. There is going to be a set of filters over here. So if any dust particles that have from the conditioned space, they have gone into the air, they will be removed. We will have a fan for the return air fan, and you will have the heating and cooling coils over here. So of course, let's first look at the return air, then we will come to those coils when we talk about the supply side. So when the return air goes into what is known as the mixing box, where the recirculated air mixes with the fresh air from outside. So as you can see, we are moving with the, if you keep an eye on the cursor, we are moving in this direction, and we have an exhaust damper over here. So part of the air which is returned from the conditioned space is exhausted. The remaining air is over here, and we have the fresh air. Again, there is a damper for fresh air that is over here, and there is again a filter after this damper on the lower side, so that any fresh air from outside, if it has dust particles, etc., those are removed. Then it goes into a energy recovery unit or a heat recovery unit, which is not necessary that it is present in all AHUs. It may be required if the customer or the client wants it, or we can ask the manufacturer not to include it in the AHU. You will look at the function of a heat recovery wheel or a heat recovery heat exchanger in the video. So the air that comes in from outside is mixed with the recirculated air in the mixing box, and then that air passes through the coils. You can have a heating coil or a cooling coil. You can have more than one coil depending on the requirement of the air which is sent to the conditioned space. And that air, if it's a cooling coil, will be. We come back to the all air central air conditioning system, and then we will look at further variations of this type of system, which are the constant air volume or the constant volume system or the variable air volume system. The constant volume system means that the volume of air, that is conditioned air, supplied to a conditioned space remains unchanged even if the load in the space changes. That means the variation in the load will be countered by changing the temperature of the air, keeping the volume supplied to the conditioned space unchanged. So the simplest of these is the single duct constant volume single zone system. It has one supply duct through which the hot or cold air will flow according to our requirement. In winter we will be using the heating coil, will provide hot air to the conditioned space. In summer we will be supplying cold air to the conditioned space. Okay. And the schematic diagram is shown to you over here. So you can see that we have the cooling coil, the heating coil. You might also have a humidifier over here, or it's shown over here in this schematic diagram. And you have the supply duct, then you have the return duct. Part of the return air is exhausted, the recirculated air is mixed with outside air, then it is passed through the cooling or heating coil as required. The on the psychrometric chart, the cooling cycle that we had looked at earlier will apply to this particular arrangement. It has certain advantages and disadvantages, which are listed over here because it's the simplest of the designs. It has a low first cost and maintenance is easy, but again the restriction is that it can condition only one zone. It is not suitable for multiple zones, and if there is a change in the requirement of a building from a single zone system to a multiple zone system, this type of a system, if we have installed it, would not be easily modified. It will be probably better to shift to a proper multi-zone system, which we are going to look at as we move through this discussion. So now let's look at that possibility that we still have a single duct and a constant volume system, but this time it is a system which will serve multiple zones. And for simplicity, in the schematic diagram I have shown two zones. There can be more than two zones, and this type of arrangement is known as a terminal reheat system, in which we can see that there before each of the zone there is what is known as a reheat coil, and the purpose of the reheat coil is to provide energy to the air which comes from the cooling coil according to the zone requirement. Okay. Now let's say at state 6, after the cooling coil, we have the air coming in at 12 degrees C, and we need to supply the air to zone A, which we are keeping at let's say 24 degrees C, whereas zone B is going to be maintained at a lower temperature. Or we will maintain it at a higher temperature. You will see the reason why I'm saying that. Let's say we are going to maintain it at 26 degrees C. So that means the air that we are supplying over here, let's say we need to supply it at a temperature of 18 degrees C. That I will also mention over here. And the supply temperature to zone B, let's say that is higher, that will (20 degrees C). So the supply of air at state 1A is at 18 degrees C, and the space is going to be maintained at 24 degrees C. The supply of air at state 1B to zone B is at 20 degrees C, and zone B is maintained at 26 degrees C. What we have done, we have cooled the air to 12 degrees C. Now this reheat coil will heat up the air from 12 degrees C to 18 degrees C, and similarly it will heat up the air that comes at 12 degrees C to 20 degrees C for zone B. So that by this use of reheat coils we are able to meet the requirements of multiple zones. For example, again, if we want to look at what happens if the load in zone A increases. If the load in zone A increases, it means that this temperature will begin to rise, and what we will want is, if we want to keep it at 24 degrees C, the supply A temperature will have to be reduced from 18 degrees C to, let's say, 15 degrees C. So that means the amount of heating that we were providing in the reheat coil will be reduced, and then again we will be supplying air at a lower temperature to counteract the increase in the load. On the other hand, if the load decreases, this temperature will start to drop. That means we will have to supply the air at a higher temperature. So we will add reheat in the coil, and then again we will balance the load variation in the zone. The same is now shown on the psychrometric chart. Okay, I will just reduce it a little so we can look at it, the schematic as well as the psychrometric diagram, which shows the cooling cycle for a terminal reheat system with two zones. You can see this 671, state 671, they are all the same, so they are shown over here. That is after the cooling coil. Then state 1A and state 1B, they are going to be different, and I've shown that temperature at 1A was less, 18 degrees C, and that's why by looking at it I had said that the temperature at state 1B will be higher. So you can see the dry bulb temperature at 1A is lower than the dry bulb temperature at 1B, and because the reheat coil only sensibly heats the air, so the process is shown over here. There is sensible heating from state 6 to state 1A, and there is sensible heating from state 6 to state 1B for each of the two zones. Then from state 1A the air goes into zone A, and from here it goes into zone B. So these two lines over here, this line over here for example, is the space condition line or the load ratio line for zone A. Similarly, this line over here is the space condition line for zone B. And you can see due to the load there is a increase in the dry bulb temperature and humidity ratio. That means there is both a sensible and latent load. Similarly for zone B. Then the air that is returned from zone A and zone B, the two streams are combined together and the resultant state will be 2. So we have adiabatic mixing of states 2A and 2B to give us the resultant state 2, and that means state 2 will lie on the straight line connecting zone states 2A and 2B. So you can see state 2 over here. The air that is exhausted, we are labeled it as 3, but the state 2 and 3 is the same because the exhausted air is the same as the returned air in terms of the state. Then the returned air, the recirculated air is mixed with the outside air. So the outside air is at state 4. You can see state 4, higher temperature, higher humidity ratio. Outside air at state 4 mixes with the recirculated air at state 2 or state 3, you can say they are the same, to give us the mixed condition at state 5. Then that air which is at state 5 is cooled and dehumidified. This is the cooling and dehumidification process, and when we get back to state 6. That is how this psychrometric diagram shows the cooling cycle of a terminal reheat system. And if you are given a problem, you can solve it in the usual manner. That is, our objective will be to first locate as many state points as possible so that we complete the cycle, and once we have done that, we can extract any further information that is required. Then the advantages and disadvantages of this type of a system, the terminal reheat system, is also given to you. Relatively small, less space is required. Temperature and humidity control is very good, and it is flexible, and reheat can be added or removed according to the change in the load in the zone. But the prime disadvantage is the energy cost. It is expensive to operate, so it's energy inefficient, and for this particular reason, especially these days when there is a great emphasis on energy conservation, the use of these systems are quite strictly regulated by most energy codes and standards all across the globe. We will now move on to the second type of a multiple zone system with again a constant air volume, and that is known as the dual duct constant volume multiple zone system. And the name dual duct comes from the fact that instead of a single duct supplying air to the conditioned zone, we have two ducts. One will carry cold air and the other warm air from the air handling unit to the conditioned space. And how this works, once we look at the schematic diagram, you will be able to understand that. First, look at the schematic diagram. You can see, because we have two ducts, one will have cold air, so there's a cooling coil for that. The other will have a heating coil for generating warm air, and it might also have a humidifier. If the humidifier is not there, we can again still have a heater, and that will still be a dual duct system. So if you look at state 6, the air that we have at state 6 is divided into two streams. One goes over to the cooling coil, the other goes to the heating coil, and we have the two zones again over here shown, and I will again put in some numbers over here to say, let's say the temperature is so much over here, and I want a different temperature over here, and I'll just quickly take a look at the diagram over here to see zone 1B, 1A, 2A and 2B. 2B is higher, so we will say that this is again 26 degree C. Okay, I think we can leave it like this. And again, we will be supplying air to zone A at a lower temperature and to zone B at a higher temperature. If this is 17 degrees C, and we will supply air to zone B at a higher temperature, 21 degrees C. The air coming from the cooling coil, again I need to just give some numbers. We have 14 degrees C over here, and the air that is heated and humidified has a higher temperature, 40 degrees C. What we want to do is now provide air to zone A at 17 and zone B at 21 degrees C respectively. What we will do is that the air that we are supplying from the cooling coil will be mixed with the air coming from the heating coil in a mixing box, and by changing the proportion of the air in this mixing box, we can control the supply temperature to a particular zone. The same applies to zone B. For example, again, if the load in zone A increases, it means this temperature will start to increase, and we will have to reduce the temperature to zone A, and that can be done by reducing the amount of warm air and increasing the amount of cold air, such that the volume flow rate into the zone does not change, but the proportions of cold and hot air can be varied, and that way we can vary the temperature of the supply air to the zone according to the zone load requirements, and the same will apply to zone B. Again, I will show you the schematic diagram and the cooling cycle on the psychrometric chart, and we will again start with the cooling coil position, that is 7, and we will look at the coil position 9, which is for the heating coil. You can see that in the mixing box the two streams are adiabatically mixed, so the resultant state will lie on a straight line connecting states 7 and 9. So you can see state 9 and state 7. The resultant state for zone A is 1A, and the resultant state for zone B is 1B, and both these states are obtained by the adiabatic mixing of states 7 and 9, so those must lie on the straight line connecting 7 and 9. So you can see 1B and 1A, and 1B sorry 1A and 1b. I think I need to, according to this diagram over here, 1a is higher and 1b is lower. So this temperature over here, if it is 24, maybe this will be, you can say this is going to be 22. We can change that value. Let me change this value so that it is in line with the psychrometric diagram, and this will then be, let's say, call it 15 degrees C, or let's say 16 degrees C. Okay, now if you look at these two values over here, they are consistent with the diagram that is drawn over here. Temperature 1a is higher than temperature 1b. So temperature 1a is higher than temperature 1b, though it could be the other way around. So you can have state 1b at a higher temperature and state 1a at a lower temperature. That depends on the zone conditions. Then again you have the load ratio lines, 1b to 2b, and then 1a to 2a. So that's the space condition line for the two zones. Then the return air from both the zones is mixed to give you the resultant state 2 that we can see over here. That resultant state 2 is mixed with the outside air to give us state 5. So 2 and 4 gives us state 5, and state 6 is the same, which is after passing through the fan. Now we have the division of the air into two streams. One is cooled and dehumidified, the other is heated and humidified, and those two streams are shown by the respective processes. This is first sensible heating from state 6 to state 8 when it passes over the heating coil. Then it is humidified, and the other stream, it is cooled and dehumidified to state 7. So heating and humidification to state 9, cooling and dehumidification to state 7, then these mixing of the two streams in the mixing box, which is where we started from. So that is the cooling cycle for a dual duct constant air volume multiple zone system. We will look at the advantages and disadvantages and move on to another arrangement for conditioning the multiple zones. This is type of arrangement has the advantage that it can provide simultaneous heating and cooling in different zones. So if you need heating in one zone and cooling in another zone at the same time, because we can vary the proportion of the air in the mixing box, we can do that. And again, it responds very well to variations in zone load and maintains precise conditions in the conditioned space. Indoor air quality is also maintained properly, and no seasonal changeover is necessary, that if you want to shift from winter to summer air conditioning, the same system can be seamlessly used for that. Disadvantages, of course, because there are two ducts, we need more space, and each duct has to be sized to handle the entire flow rate if required. For example, if only cold air is required, so it should be able to handle the maximum flow rate, that duct, the cold air duct, and similarly the hot air duct. And it has a high initial cost, and again energy usage is a problem because we are heating and cooling the air at the same time. It's not very energy efficient. We now move on to the other arrangement that you will see is the one that we used in modern air conditioning systems, which is known as the variable air volume system, and it is suitable for multiple zones. In a variable air volume system, as the name implies, the quantity of air that is supplied to the zone can be varied, whereas the temperature is kept constant. Previously we were keeping the quantity of air constant and varying the temperature. It's the other way around in the case of a VAV system. And to ensure that the volume flow rate to the zone can be varied, we need a unit that is known as a VAV unit, or a variable air volume unit, or a VAV box, which will allow us to vary the volume flow rate to the zone. And yet again, we have the schematic diagram over here, and at the same time I will try to show you the cooling cycle drawn on the cyclometric diagram. You can see after the cooling coil we have state 7, and the air goes at state 7 into both the zones. So we have air going into both the zones at the same state. It's only the volume flow rate is different, but again, because the zone loads are different, sensible and latent loads can be different, the space condition lines for the two zones will have different slopes that you can see from state 1, from 1A to 2A for zone A, and 1B to 2B. Then the return air is combined from the two zones to give us state 2. That return air, part of it is exhausted, and then it is mixed with the outside air, which is at state 4, to give us state 5, and state 6 is the same after passing through the fan, and then it passes over the coil. It is cooled and dehumidified. So it's similar to the cycle for the basic cooling cycle that we had looked at, but the difference this time, of course, is that we are handling two zones, and so this portion will show that difference over here. And we can move on to the advantages and disadvantages of this type of a system. You can see that the principal advantage is its lower energy consumption even during partial load conditions, and that also leads to lower fan power consumption. So there are system savings when we use a variable air volume system, and that is why modern air conditioning plants extensively use this sort of a system. Temperature controls in both the interior and external zones can be carried out very well, and we can also shift the air flows from one zone to another according to any change in the requirements. Disadvantages: we have a high initial cost, but because it's very energy efficient, that high energy cost, initial cost, pays back in a short duration. Because we are reducing the air flow rate in the conditioned space, if the load changes, it might also cause deterioration of the indoor air quality at very low loads, because the air flow rates will have to be reduced. That means the amount of outside air or the fresh air, that proportion will reduce, and the air quality inside might not be maintained. So that could be a consideration that we have to keep in mind. So the same is that when we have low loads, because the volume flow rates of air is low, the distribution of the air in the conditioned space may not also be carried out in the manner that it is desired to be. And humidity control under widely varying latent loads is difficult, although not impossible, but it becomes difficult if the variation is too large. I will now show you an actual VAV box and how it is connected to the supply duct. So if you look at this is the supply duct over here, and in this supply duct at the end before the zone, you can see the VAV box, and this is a close-up look of the VAV box. This is where it will be connected to the supply duct. So there's a airflow sensor over here, and there will be a damper inside. So this is the actuator to open or close the damper. This is the control system over here, and we are going to look at a labeled schematic of the same. So you have the velocity sensor, you will have a flow damper, which can open and close to increase or decrease the volume flow rate going into the conditioned space. And this box is primarily to reduce the noise as the air passes through this damper. We have the control system over here along with the actuator, and if required, some of these VAV boxes also have a reheat option, so you can provide a reheat option, although it is not necessary. Sometimes you can do that, but it does not provide too much of a reheat. It has limited capacity for reheat. This is how we can vary the volume flow rate through into the conditioned zone. So I have placed a question at the end. This is for a terminal reheat system, and it is left as an exercise for you to solve this question. And as I mentioned earlier, the procedure will be of course similar to that of a cooling cycle that we had gone through earlier, that we need to locate the states and develop the entire cooling cycle, and once we have that, we can then extract the desired answers as we proceed with the solution of the problem. And that is all for this lecture, and we will continue with a new topic in the next lecture.